This section is on independence and the multiplication rule. The objectives here are to identify independent events, use the multiplication rule for independent events, and then also to compute at least probabilities. Okay. All right, so in the last section we talked about the addition rule, and that shows us how to compute OR probabilities, right? That was a probability of an event E or F with certain conditions, right? Whether it's disjoint or not disjoint. The multiplication rule in this section, we're going to deal with AND probabilities, the probability of E and F, also under some sort of conditions. And those conditions will be whether the two events are independent or not independent or dependent. All right, so let's discuss independence. We see that two events are independent if the occurrence of one event does not affect the probability of the second event. And we would say that two events would be dependent if the occurrence of one event does affect the probability of the second event. Now, for example, if we have a deck of 52 cards, and I ask you, what's the probability of pulling a king? Well, you say, well, there's 4 kings out of the 52, so that's the probability, right? But if you don't replace the card back into the deck, right? If you hold on to that card and then you choose another card, well, you no longer have 52 cards. You actually only have 51 cards. Okay, and if I were to ask you what's the probability of getting a king again, well, you already took out a king, so it'll be 3 out of the 51. Okay, so you see how those two events would be dependent on each other because the occurrence of one event, the first event, had an effect on the second event. Okay. So very quickly here, we're going to talk about disjoint events again. Now, disjoint events happen to be dependent. You might think, well, if they're completely mutually exclusive, then how are they dependent on each other? Well, it has to do with if you know one event happens, you know that the other one did not happen at all because they're completely disjoint. So that's the idea behind that. Okay, so for example, selecting a single card from a playing card deck, event Q getting a queen, event K getting a king. Since kings and queens are disjoint, right, there's no card that's both a king and a queen, then the probability of getting a king and a queen in one card is 0. Therefore, if we pull a king, then we know with certainty that a queen has not been pulled. Okay. Now, for independent events, well, that implies that event E does not affect the probability of event F. Okay. Example, selecting 2 cards in succession, okay, from a playing card deck with replacement. Now, that's the key word there, with replacement. That tells us that they're independent, and you'll see why. That's because you put the card back into the deck for the subsequent draw from the deck. So you still have 52 cards. So it doesn't affect the probability of any subsequent draw from the deck. So since we're pulling a card and then replacing the card back, the outcome of the first draw does not affect the second draw. Therefore, the king and queen are independent in this case. Okay. So the difference here is we're talking about within a single draw or in 2 cards in succession. All right. So a lot of times to determine if something is independent or dependent, oftentimes we require a little bit of intuition. Okay. So sometimes just by reading 2 different events, you can intuitively know if they're independent or not. So let's see if we can test our intuition here. The battery in your cell phone is dead. The batteries in your calculator are dead. Are these 2 events independent or dependent? It's a little vague, but I would say that these are 2 independent events because they don't really share the same energy source, right? They have independent batteries. Okay, an argument can be made since it's the same owner, your cell phone and your calculator, then maybe your negligence is carried over to all your devices. So it might be a little bit of dependency there, but in general, something like this would be independent. B, you learn algebra, you learn calculus. You need to know algebra to learn calculus. Right, so you do have to take those classes in succession. So these are definitely dependent because calculus is heavy on algebra. Part C, flipping the heads on a coin or rolling a 5 on a die. Well, again, you have to ask yourself, does the occurrence of one of these events have any effect on the other event? Yeah, the heads should not have any effect on the die, right? So these are definitely independent. All right, let's do an example here. It says, if Rachel draws a card, which is a spade, and does not replace the card back into the deck, find the probability that Rachel draws a heart. Okay, so in the next subsequent draw, on the second draw, she draws a heart. That's what they're asking us. Okay. If Rachel has replaced the spade before drawing that heart, how would the probability be different from when she did not replace the spade? All right, so essentially we're trying to compare the difference between the probability of drawing a heart if the first card was a spade, right, in two different situations. First one being if you replace that card back into the deck and then now you still have a fresh new deck of 52 cards, or without replacement, which means you hold on to that first card and then your second draw is from a deck of 51 cards. Okay. Later on we're going to call these conditional probabilities, but for now we'll omit that notation. Okay, so the question here is find the probability that Rachel draws a heart. Okay, so probability of a heart. Okay, and this is, well, with replacement, so second draw is out of 52 cards. Okay, and we know there's 52 in the deck, so how many hearts are there? Well, that's an entire suit, which every suit has 13 cards. All right, so this is a 1 in 4 chance of occurring. Okay, now without replacement, that just means that that second draw is out of 51 cards. Okay, the card taken out was a spade. Okay, so the probability of getting a heart on the second draw would be, well, it's out of 51. Now we took a spade out, so there's a spade that's taken out, so there's 12 spades left, but we're really concerned about hearts here. There's still 13 hearts, so this will be 13 out of 51. Okay. Now if you want to compare these with approximate decimals here, so this is actually 0.25 exactly, and this probability should actually increase because the denominator got smaller, right? So this is approximately, if I'm rounding, 0.2549, something like that. Okay, so probably did increase because there's less cards to choose from, and there's still the same amount of hearts. All right, so this leads us to the multiplication rule. Now this multiplication rule, as it stands here, only applies for independent events. Okay, and it says that the probability of E and F is the same thing as the probability of E on its own times the probability of F on its own. All right, so let's test that. So the question here is, what is the probability of Rachel drawing a queen, replacing the card, and then a spade? Okay, now again, we can only use this rule because the question here is what? Probability of a queen and a spade, right? Now we can only use this rule if the events are independent. Well, by replacing the card back, that second event is out of 52 cards. So essentially that first event had nothing to do with the second event. It didn't affect the probability. So yeah, this implies independent events. So we say that probability of getting a queen and a spade. Now these are in succession, okay? It's not asking what's the probability of a card being a spade and a queen. So I like to put a little superscript here saying queen first, spade second, to make the distinction. Okay? So here we have, well, because these are independent, right? Independent. This is just simply the probability of just getting a queen on its own times the probability of getting a spade on its own. There are 4 queens out of 52. There are 13 out of 52 spades. We can reduce these. 4 out of 52 reduces down to 1 and 13. And I do see a 13 here that I can actually cancel out with the 1 above. So we have a 1 in 52 chance of this occurring. All right, so I do want to specifically define and, the word and. Okay, so when we talk about the probability of this event and this event happening, it could be in terms of in a single trial, right, the intersection of these two sets, or it could be in succession, the probability that this happens and then this happens. Okay, so let's do an example here to kind of show you the distinction, because we're going to essentially say the same thing, but it's a little different in each case. So, example, one card is drawn from a standard deck of 52 cards. Find the probability that the card will be a heart and a diamond. Okay, so that's this first question. Now, this is just one card, so in one trial. Okay, how many cards are both a heart and a diamond? If you look at the deck of 52 cards, well, these are two different suits. No one card can have two suits. Every card only has one suit. So you would say that, well, they have none in common. There's no intersection here, so it's an impossible event. So an impossible event has a probability of 0. Okay. Now we can ask the same question: what's the probability of getting a heart and a diamond? But if it's in multiple trials, like in 2 cards in succession, then you'll see that the probability is not going to be the same as in one trial. So in multiple trials, we draw 2 cards from a deck of 52 cards. Find the probability that the first card's a heart and then the second's the diamond. All right, so this is essentially the same question, except for it's in 2 cards in succession from each other. Okay, so that's why I like to make the distinction. The probability that there's a heart on the first draw and diamond on the second draw. So this is the same thing. Well, again, these are with replacement. Card is replaced. That means these are independent events. So we can use the multiplication rule, which states that the probability of heart on first and diamond on second is the probability of getting a heart on its own times the probability of getting a diamond on its own. Okay. There are, again, every suit has 13 cards out of 52. Same thing with the diamonds here, which are 13 out of 52. And each one of these fractions is a 1/4. 1/4. Multiplying across is 1/16. Okay. So again, these two probabilities are not the same. 0 and 1/16 are not the same. And again, the distinction here is one trial versus multiple trials in succession. Example 4. Suppose we are flipping a coin and then rolling a die. Again, using a little bit of intuition, coins and dice should be independent from each other, right? What's the probability that we flip a tail and roll a 3? Again, a tail and rolling a 3. That's that probability of tail and 3. Well, again, these are independent events. The occurrence of one of these observations does not affect the occurrence of the other. So this is simply the probability of getting a tail on one coin times the probability of getting a 3 on the die. 2 different fractions. Well, a coin just has 2 sides, one of those sides being a tail, so 1 out of 2. And a die has, there's 6 sides, and there's only 1 3, so that's a 1 in 6 chance. And we can't reduce there, so we just multiply straight across and get a 1 in 12 chance of this occurring. We can extend the multiplication rule to 3 or more independent events. If you recall from the addition rule, if we had a series of disjoint events, we can do probability of A or B or C ... right? As long as they're all disjoint, we were able to add them all up. It would just be probability of A plus probability of B plus probability of C. And then there's something similar for the multiplication rule, okay? But this only works if the events are independent, okay? If you have event 1, event 2, ... all the way to the nth event, and they're all independent, then the probability of the first event and the second event and the third event all the way up to the last one is simply just the product of their individual probabilities. Okay. Let's do an example. 3 different people are randomly selected from your class. Find the probability that they are all born on a Monday. Give your answer to the nearest 10,000. That's 4 decimal places. All right, so 3 people. So we have 3 people that are randomly selected. Find the probability that they are all born on a Monday. Well, the question is probability that the first person is born on a Monday and the second person is born on a Monday, right? And the third person is also born on a Monday. Well, we have to ask ourselves, for and probability, are these independent? Well, I mean, it's possible that you can have like twins in a classroom, right? They can be taking the same class, but the fact that we're randomly selecting people, where then we say that, yeah, each one of these people that we select should be independent from each other as far as what day they were born. Okay, so this implies independence. All right, so we can just use the rule that we just found out about right now for multiplication rule of n independent events. So there's a probability that the first person is born on Monday times the second on a Monday times the third on the Monday, right? And there's only 7 days in the week, so this is a 1 in 7 chance for all of them, which is a 1 in 343. They did specifically ask us to round. If you punch this into the calculator, you get something like 0.0029. Next example, the probability that a randomly selected 24-year-old will survive the year is 0.9986. So statistics like this, which deal with surviving the next year, these are really useful in pricing life insurance and also pensions for that matter, where they need to calculate the probability of people surviving. Okay, that way they can price out insurance accordingly. What is the probability that 3 randomly selected 24-year-old males will survive the next year? Give your answer to the nearest 10,000. Again, that's 4 decimal places. All right, so again, the probability that 3 randomly selected 24-year-old males will all survive. Okay, that means the first person survives and the second person survives and the third person survives. Okay, so again, this is an and probability. I can say survive on the first person and survive on the second person and survive on the third person. Okay. Again, we have to ask ourselves, are these independent events? Well, again, here's that word randomly. These 3 people were randomly selected. Again, independence means that the occurrence of one of these events does not affect the occurrence of the other. So if one person survives, it doesn't affect the other, the survival of the other 2 people, and vice versa. So yeah, these are definitely independent. So it's probability of survive times probability of survive times the probability of survive. And they told us that that probability is 0.9986. So we have 3 of those. And we can write it, since the same factor repeated 3 times, we can raise it to the 3rd power. You can punch that into your calculator. And they did ask us to round this to the 4th decimal place here. And you'll get 0.9958. Okay, this next part is all about computing at least probabilities. Okay, specifically at least 1. Okay, so this phrase at least really just means greater than or equal to. Okay, so for example, if they say at least 1, well, at least 1 means 1 or more, correct? So the probability of 1 or 2 or 3 or 4 or ... to whatever the maximum number may be. Okay, so we're going to have to use a little bit of clever math here to figure out this formula. Now here is a a template and essentially the formula that we're going to use, but I'm going to go through the explanation of where this comes from with an example. Okay, so we can use a complement rule. So we know that at least one means one or more. And what are we essentially leaving out? Well, we're actually leaving out the probability of 0. So we say that the probability of 0 and 1 or more are complements of each other. So the probability of 1 or more is equal to 1 minus the probability of none. Okay, so this would be a template for calculating these probabilities. Okay, so let me explain that in more detail with an example. That way it makes a little bit more sense. So if we were to say, what's the probability of at least one head out of the 5 coins? So we have 5 coins that we're tossing, and what's the probability that we have at least one? So either 1 or 2 or 3 or 4 or up to 5, which would be the maximum. Okay, so let me actually just draw a probability distribution table for that. Okay, we have X, which is the number of heads in 5 coins. Again, and then the probability of X. Okay, now the smallest number this can be is, well, 0, because you can have essentially 0 heads. That means that all the coins came out to be tails. That should be a pretty rare occurrence, but that's possible. You can have 1 head, 4 tails. You can have 2 heads, 3 tails. You can have 3 heads and 2 tails. You can have 4 heads and 1 tail, and then you can have 5 heads and 0 tails. That's also another rare occurrence. Okay. Now we haven't gone through the probabilities of each one of these events. We haven't gone through the how to calculate that. We will soon when we get into binomial, but we haven't talked about this. Okay. Now each one of these has an probability associated with it. Okay, and we will learn eventually how to calculate these. What we do know is for any probability distribution, the sum of all these individual probabilities of each outcome has to add up to be 1, right? The sum of the probabilities has to be 1. Okay, now again the question is at least 1, so they're really asking for these ones, 1 or more. Probability of at least 1 is 1 or more, right? Now you notice some of you have probably already seen this, right? And then this one right here would be essentially the probability of none. Okay, so doesn't that make sense that if all these probabilities add up to 1, then wouldn't this equal to 1 minus the complement, which is none? Now it turns out that these two probabilities are actually pretty easy to calculate. The one for 0 and then the one for 5. Okay, the ones in the middle are a little bit more complicated and we haven't gotten to that. Okay, so that's why we're able to use this little clever trick here. Okay, because the probability of none is actually pretty easy to calculate. So in our case, the probability of none, well, none are heads. That means they're all tails, right? So all of them being tails, these are all independent coins. You could say that they're 1/2 times 1/2. You need 5 of these. All right, these are 5 coins here. Five coins. And that's the same factor to the 5th power. That'll be 1 minus 1 over 32, which is 32 over 32 minus 1 over 32, which equals 31 out of 32. Okay, so it's a pretty high chance of getting at least 1 head out of the 5 coins. Okay, the probability of getting none is 1 in 32. It's very unlikely to get 0 heads after you toss 5 coins. But the probability of getting 1 or more is 31 out of 32, pretty high chance. Okay, next example. Only about 3% of male high school basketball players receive an athletic scholarship to play NCAA Division I basketball. If 5 male high school basketball players are selected at random, what is the probability that at least one of them will receive an athletic scholarship to play NCAA Division I basketball? All right, so they're giving us a little bit of information. They're saying that for any one person or male high school basketball player, there's a 3% chance of them actually getting that scholarship. Okay. And the question here is, if 5 high school basketball players are randomly selected, what's the probability that at least one of them will receive the scholarship? Okay, this is one of those at least one probability. So probability that at least one out of the 5 gets scholarship. Well, from the template above, we know that this is the same thing as 1 minus the probability that none of them get a scholarship. None of the 5 get a scholarship, because these are complements of each other. Now, if the probability of getting a scholarship for one person is 3%, we'll write it up here. All right, 0.03. Then that tells us the probability of not getting a scholarship, which is this complement. I can say no scholarship. Well, that's a complement at 1 minus 0.03, which is 0.97. A 97% chance of you just not getting a scholarship. Okay. All right, so again, going back to this, we have 1 minus the probability that none of the 5 get a scholarship. And again, we know these are independent events because they are selected at random here. Okay. So of 5 independent events occurring all at the same time, well, it's the product of their probabilities. So the probability of not getting a scholarship for all 5 of them is 0.97 times 0.97 for the second one times 0.97 for the third, 0.97 for the fourth, and finally 0.97 for the fifth. And of course, you can write that in a more concise format as 1 minus 0.97 to the 5th power. If you put that into your calculator, you would get 0.1413, rounded to 4 decimal places. It didn't really specify, but that's what it would be. Right. So the probability that one person gets a scholarship is 3%. But if you have 5 people, and the probability that any one of those will get a scholarship, so this person or this person or this person or this person or these 2 people or these 3 people and so forth, well, it increases your probability, right? You essentially have more attempts at getting at least one person that gets a scholarship. Next example. This one's already done for us here. But it says, you have 50 DVDs. This particular brand has a 0.5% defective rate. So 0.5% of all DVDs are defective. It's actually pretty high, you'll see. Therefore, the probability of a disc being defective is 0.005. That's just 0.5% converted into a decimal format. And therefore, the probability of a disc being good is 0.995, right? These are complements of each other. Right. The question here is, what's the probability that at least one of the 50 DVDs is defective? Round decimal to 3 decimal places. All right, so again, you own 50 DVDs. There's a 0.5% chance that one of these DVDs is defective. And the question is, what's the probability that you have at least one of these DVDs defective? So if you just use the template, we have the probability of at least one of the 50 DVDs is defective is equal to 1 minus none of the 50 DVDs are defective, which the next line, the next jump is essentially saying the same thing. None of the 50 DVDs are defective is the same thing as saying all of the 50 DVDs are good. Those are the same phrases, essentially. They're equivalent phrases. If they're all good, the probability of being good is 0.995, and you would have to do that for all 50 independent DVDs. Okay, and then that would be to the 50th power, and you get a 0.222 chance of getting at least one of your DVDs defective. So there's a 22.2% chance out of the 50 DVDs that you have, at least one of them is defective. Now, in some cases, it can be very cumbersome and tedious to always treat things as dependent events. And for that reason, oftentimes it's better to treat dependent events as independent, because treating things as independent are actually a lot easier to deal with. But this can't be done all the time. Okay, there's a certain guideline in which you can actually apply this. Okay, so let me just read this. Treating dependent events as independent. So some calculations are cumbersome, but they can be made manageable by using the common practice of treating events as independent when small samples are drawn from large populations. Okay, so the idea here is you have to take a small sample out of a large population, and in such cases it's rare to select the same item twice. Okay, as you'll see in the example that we're going to see. Okay, so even if you replace it back into the population, it's very unlikely that you'll get that item again. So it's the same as actually not replacing it back into the population. Okay, so that's the basic idea of this. So as long as that sample is very tiny, so that the chances is very unlikely that you just get that sample again, then you can treat dependent events as independent. And how tiny? Well, we have a 5% guideline. Okay, so if a sample size is no more than 5% the size of the population, treat the selections as being independent, even if the selections are made without replacement. So they are technically dependent. Okay, so they're technically dependent, but the thing is, they're so small that even if you replace it back into the population or not, any subsequent events will essentially be unaffected. Okay, you'll see from the next example a little demonstration of how different the probabilities will be if you treat them as dependent versus independent. Okay, they will be different, but just not by much. All right, so in this case we have 3 different watches are randomly picked in succession without replacement. Okay, so that means these are dependent events, right? You're not replacing the watch back into the box for every subsequent selection. All right, so we have a box of 65 watches in which 11 are defective and 54 are essentially good. Okay. The question here is, what's the probability that at least one of the 3 watches has no defects? Basically, what's the probability that they're all good? Round to 3 decimal places. All right, so what we have here is we have the probability that the watches have no defects, or they're good. That's the same as saying as 1 minus the probability that the 3 watches, that none of the 3 watches are good. Okay, which means 1 minus the probability that they're all defective. Okay, now these again are dependent events. So to figure out, we have the first watch, second watch, and then third watch. Okay, I'm going to draw a little table here. We have defective, we have good watches, and then we have total. All right, in the first selection, we have a total of 65 watches. They told us that there are 11 that are defective and 54 are good. Okay, so again, the probability of getting a good watch, or essentially not a good watch, but that all 3 watches are defective, well, the first one being defective is 11 out of 65, so that's this fraction. And then we move over to the second selection. Again, we're not replacing that watch back into the box, so the probability does change. The probability of getting a defective watch changes from, well, let's see. We no longer have a total of 65. We have 64. We have 1 less defective because we already took out 1. We still have 54 good ones. So the probability of getting a defective one is now 10 out of 64. Okay. And then you can see the pattern here. There's 1 less defective one. Was 1 less total. There's still 54 good ones. So the probability of getting the defective one is 9 out of 63. Now these fractions really aren't that different from each other, and you'll see why. Okay, if you do the math here and you multiply them all out, you can get this number. Okay, so it can be kind of tedious to figure out those probabilities if they're dependent events. So you would have to create some sort of table like this and figure out what the numerator and denominator is. Okay, now in this case we took 3 watches out of a population of 65. Okay, we're taking 3 watches out of a population of 65. And if you were to divide those two, you would get 4.6%, which is less than 5%. So by the 5% rule, we can treat these dependent events that are technically dependent as independent. And what do I mean by that? Well, we can treat them as if we were replacing it back in each time. So we can treat it as 11 out of 65, all 3 selections. So that's what we do here, right? That right there is 1 minus 11 out of 65 times 11 out of 65 times 11 out of 65. And if you do that math, you'll get this as your answer. Okay, and these are close enough. And the reason for that is because our samples are less than 5% of the population. Okay, so in some cases you can just treat events as independent even though they're technically dependent. Okay, and so it's that 5% rule.